Okay, so let me start by introducing today's speaker. Today's speaker is Dr. Aharon Brodutch. Aharon obtained his PhD on locality and the flow of quantum information in 2012 at Macquarie University in Australia. After his PhD, Aharon went on to become a postdoctoral fellow at the Institute for Quantum Computing in Waterloo, Canada, and then a postdoctoral fellow at the University of Toronto. In 2020, he founded Entangled Networks, a startup that provides solutions for multi-QPU quantum computers and aims at supporting scalability of quantum computers. Today, Aharon will tell us about how a modular architecture of quantum computers with interconnects linking each QPU is within reach of current technologies and could provide near-term solutions to scalability. So we're very excited to hear more, and with that, the virtual floor is yours.
Yeah, thanks. Thanks very much first for giving me the opportunity to talk. The list of speakers in your conference is pretty amazing. So I'm happy to be among them, or in your seminar series, I guess. Yeah, so my name is Aharon. I'm the CEO of Entangled Networks. We are a startup building solutions for multi-core quantum computing, and that's what I'm going to talk about. I'll start by sharing the screen. Let's see. Okay, everything works. Yeah, and so before I start, I just want to say, maybe even before introducing this slide, that I've already told Hugo I'd be very happy to take questions as I talk rather than just at the end. There are versions of this talk on YouTube, and so this would be kind of boring if I didn't get questions. And the next thing I want to say is that the work you're going to see was done by a bunch of people who are not me. So all of our people at Entangled Networks. So we're based in Toronto, and all of these guys show up at the office and do the hard work. And like I said earlier, what we're building is solutions for multi-core quantum computing. And so that includes hardware that allows multiple quantum computers to be connected together. And I'll talk about that hardware, and also software that allows everything to work as one machine. And I'll also talk about that software. You know, we are a commercial company, and so I am trying to sell you something, but I'm not trying to sell necessarily a product. I'm trying to sell an idea, and the idea is the idea of optical interconnects and the fact that they can be used pretty much today to get a boost in computational power on a quantum computer. And just roughly as an outline, I'll be first convincing you that we need modular solutions. And then I'll go into talking about how we build a modular solution using an optical interconnect, which is one possible method. It's the most scalable method. And then I'll convince you, or try to convince you, that the minimal requirements are not that high for this piece of equipment. But I want to start with something that really everyone knows. But maybe not everyone has thought deeply enough about it. And the first piece of information that I'm sure everyone knows is that a quantum computer with n qubits spans a Hilbert space that has a dimension of 2 to the n. And it's huge. But that's not enough. That is not enough to give us computational power. Just having these states is great, but you need to somehow be able to access that huge Hilbert space. You need to be able to probe various areas or a large enough subset of states to really make this useful. And what happens in quantum mechanics is that you can do that without an exponential overhead. If you have a Hamiltonian that just has a polynomial number of terms in the number of qubits, that Hamiltonian can reach pretty exotic states. And initially, when people started doing quantum mechanics, this was seen as a huge problem. This was even in sort of the Solvay conference in 1927. People were noting that this, if quantum mechanics is the correct description, at the time it did seem like the correct description of physics, we're going to face a huge calculational problem. It's just hard to calculate this exponentially large, exponentially large states. So the number of terms is huge. And the problem is not just that the number of terms is huge, but you can get to this huge number of terms very, very quickly with a fairly simple Hamiltonian. But turned out that this is actually great if you're trying to use the machine in order to do computation, because now you have a machine that can fairly easily explore this huge space, and you can exploit that. And we sort of all know the story of how quantum computers evolved, from quantum simulations and ideas about exploring this huge Hilbert space. But this also creates a huge problem. And the problem is that there's an exponential space for things to go wrong. There's just a ton of stuff that can go wrong in a quantum computer. And the way we try to get around it conceptually is we kind of assume that when we talk about qubits, they are isolated. Qubit number 7 doesn't talk to qubit number 15 unless we turn on an interaction. And when we turn on that interaction, in our head, we're thinking that interaction involves only qubit number 7 and qubit number 13. It doesn't involve qubit number 8, which we didn't want to talk to. In practice, that's never true. And so, we're conceptually thinking about these small systems that are isolated, but in practice, we don't have these systems. And this is a huge problem. And the way to get around it is to make sure that we do have small systems that are fairly isolated, that we can characterize very well. And we can take these systems and get them to interact through very long-range interactions so that they don't interact when we don't want them to. Now, the problems are not just that the systems interact with each other. This is, sort of the example problem. But, if you think of a superconducting qubit, for example, you just have to put a lot of wires in a device, and those wires just start interfering with each other and with the qubits, etc. And when you think of ion traps, you need to cool everything down to the ground state, and you need to control a huge number of modes. Things just become more and more difficult as the system goes. And then there's two other pieces. One is testing. If we want to characterize a device that has 1,000 qubits, that is impossible. It is impossible to do it precisely. What we usually do is randomized benchmarking. And randomized benchmarking, in most cases, has an underlying assumption that there isn't too much interfering between the qubits. So when we talk to qubit numbers, when we do randomized benchmarking on qubit number 7, we don't need to really worry about what's happening on qubit number 15 that's somewhere distant. But again, that's just not true in practice. And so the situation right now is that we do have some quantum processors. People are making a lot of progress in different directions, but these directions, they're going in different ways. One is trying to solve a lot of engineering problems, and you solve engineering problems by building larger and larger processors, but they're not necessarily better. And you can see this with IBM going to 127, and they just announced a 433 qubit machine. But if we look at that 127 qubit machine that IBM has, we know that it doesn't perform as well as 2 generations back machine that has only 27 qubits. So the smaller 27 qubit device is actually more powerful than the larger one. And again, the reason is that more qubits are just harder to control. And so we can look at various roadmaps and that are in industry, and each roadmap has kind of a point. In the case of Google, this is a projection, but other roadmaps have more clear points where they say going beyond this point or reaching this point would require a modular architecture. We just cannot do this on a single chip. So everybody knows this, and the question is, when do we move to a modular architecture, and how? Any questions at this point? No.
No, everything is clear so far.
Okay. So IBM are fairly transparent with a lot of their plans. And so it's very nice to look at what they're doing because we can kind of see where they envision the future. So they have this roadmap that's been advertised, and they also came out with this very beautiful paper, which I really recommend reading. It is almost completely non-technical, but it outlines kind of their vision on how to scale up superconducting quantum computers. And so most of what I'm going to talk about is not going to be about superconducting, but I think this is a nice example. And what they're looking at is different ways to do modular solutions. And so the first generation of modular solutions is a bunch of quantum processors that talk to each other classically. So there's just classical communication lines between them. You cannot entangle two of these processors together. There are ways to use this in order to get more qubits than you have in a single device. So say you have a single 27 qubit device, but you have a problem that requires 35 qubits. How do you deal with that problem? And they have methods so they're building methods, not only IBM, a lot of people are working on methods to do this. And everything becomes a lot faster when the computers can actually communicate with each other classically. But the exponential advantage that we get from a quantum computer is essentially exponential in the largest single processor that we have. So if we have a 27 qubit machine and another 27 qubit machine, we're getting like the 2 to the 27 size Hilbert space. We're not, the other processor doesn't really add to the Hilbert space, or doesn't add a lot to the Hilbert space, but it does allow us to sort of iterate. And then the way we kind of get this extra power is by calling it a number of times, but that number is exponentially the extra qubits we want to add. So if we want to get from 27 to 30, we would have to call it roughly 8 times. I mean, 8 here is, or say 2 to the n times. And so that's one solution. This is, in the short term, this seems like a great solution, until we get to the point where we can connect things. Now, the first way to connect things in a superconducting machine is to take 2 chips, put them in the same fridge, put them really close to each other, and have communication lines between them. And this is what we're seeing here. These communication lines are already going to be less reliable than the communication lines that you see between the qubits, but they're going to be pretty good. You can because everything is on a single chip, you can get pretty good transmission of microwaves. What we do see here is that there is a little bit of a bottleneck, because now the connectivity map on this architecture is not what it was on the on the single chip architecture. And so we need to deal with this bottleneck, but it's not huge. The next phase is having quantum communication through a microwave link. And so if you want to do this, everything has to remain very, very cold. And so ideally you want to do this in the same fridge, but at some point the fridge can't continue handling more and more qubits. And so you have to do things across fridges, in which case you need this communication line to be very cold. And now you can really see the bottleneck happening here. There's one communication line, or there's a few communication lines happening between these pretty large chips. And the communication is rigid. You cannot do a lot of routing here. So each qubit has sort of one target qubit on the other side. But this is a good intermediate solution. But where you want to be at the end is with optical interconnects. And what optical interconnects would allow you in a superconducting architecture is to go outside the fridge from one fridge to the next. And so now you can kind of imagine this farm of these ginormous fridges, but you have thousands of them in order to create a quantum computer. It's bulky, but it works, or it should work. What we're not seeing in this picture, which is important, is once you get things into optics, you can use optical switches to move things around. And now the modular device doesn't have a rigid topology. We can kind of change topology as we go, even during the computation. And so this really looks like a classical kind of network that we have when we do supercomputers, for example. So this is where we want to be eventually. It just allows a ton of flexibility. That when you have millions of qubits, you just want that flexibility. Okay, I'll pause again for questions.
There are no questions in the chat, but I have a quick question. So this optical connection of fridges together, you paint this picture of a farm of fridges all in the same location, but because they're optical connects, they wouldn't have to be in the same location. They could be arbitrarily far apart, right?
Yeah, okay, good question. So if you keep them fairly close to each other, then you're not too worried about photon loss along the lines. If you start going further and further away, you have to think about ways to mitigate photon loss. And that would usually be done using quantum repeaters. So then you're adding another complication.
But so connecting these fridges together, how different would this be to an idea of a quantum internet that connects different quantum computers together?
Yeah,
or is it similar, but on a sort of lab scale internet?
It has a lot of similarities. Apart from the possibly needing repeaters, the hardware is essentially the same. Where it's different, and this is a very important point, is that when you're doing things on the internet, you really sort of conceptually think about someone doing something on one side and then someone doing something on the other side, and they're talking to each other. When you think of a supercomputer, just think classically now, when you think of a supercomputer that's built up of 1 million cores, all those cores need to work together towards a single task. And so what you're trying to do is to parallelize the work. You're trying to reduce communication as much as possible. And so from a software perspective, from a protocol perspective, it is a very, very different challenge. The internet versus the multi-core computing.
And so your network here, you'd want to, I guess, in a software optimization way, you have the optical interconnects, but computationally you want to minimize the amount of times they're used.
That's right. That's right. You at the end, you want the computation to happen as fast as possible. You identify your main bottleneck, which is these interconnects, and so you just want them to be able to, one, pass information as fast as possible, and two, use them as few times as possible. And again, this is classically, people are doing this all the time with supercomputers, right? When you try to program for a machine with 1 million cores, you try to optimize over similar things. But there are big differences that I'll point out in a bit.
Right. I have another question from the chat before you keep going. So what is the ratio of in-fridge fidelity to cross-fridge fidelity for this to make sense?
Yeah. Oh, so I'll it's a fantastic question. I'll talk a little bit about it at the end.
Okay.
That is a very good question. In fact, it's kind of related to my next slide. So what do we not know? And it turns out that we don't know very much when it comes to these kinds of questions. The first question that might come to mind is, what's the largest possible monolithic processor that continues making sense, right? So I want to continue growing my number of qubits on a single device, but I want to grow them in a point where adding more qubits, the noise I'm adding doesn't disadvantage me in a way that growing doesn't make sense in them. And no one has an answer to this. It's an incredibly complicated question. And it's related to the next question, which is, what are the trade-offs? Even that is something people don't really know. The quantum computers are just incredibly hard to characterize. And what happens today, both in industry and certainly in academia, is that when you build a quantum computer, that machine is a prototype, and you never build another device sort of on the same design. And so it's very hard for us to understand where we can get trade-offs. And so this is a huge question that's open. But let's say we figure this out, and we kind of know what's the largest one, and we know what the trade-offs are. And now I give you an interconnect, and I say, this interconnect works with whatever specifications we have. It has a certain speed and a certain fidelity. What's the biggest processor I want before I want to step outside? That's another big open question. Again, no one has an answer here. And then if I give you a particular modality, let's say superconducting qubits or ion traps, neutral atoms, and different types of interconnects. Now I want to ask a bigger question, which is, what does the network look like? What's the optimal kind of network that I want? And here maybe there's an emphasis on variety of interconnects, because in many cases, and you can see it here, there is not just going to be one interconnect in the device. We're going to have some optical and some of these microwave and some of these on chip. And so the network is incredibly complicated. And again, we can think of like a classical problem, right? How many cores do you want per machine on, let's say you're building a supercomputer. Each CPU will have multiple cores, and each rack would have multiple of these, and different racks would be connected over longer distances. We need to understand, how everything works together. And when we understand the network, we need to understand what the bottlenecks are. What's the thing we need to solve for most in order to get this to work faster? And this is where software comes in, software protocols, in order to alleviate these bottlenecks. And at Entangled Networks, we're kind of working on all of these problems, and they're hard. they're big research problems. So I'll give some of our insights into these questions later. Are we good?
I have another question, if you don't mind. So how much, and this is another question from the chat, how much of the compartmentalizing design is based on hardware and how much is algorithm specific?
Yeah, so that's a good question. I think today if we identify an algorithm that is very promising, which I don't think anyone has yet, it would be good to start in focusing on that algorithm. But at the moment, most of what we're doing is focused more on the hardware than on the algorithm. But again, I'll show some results, and you'll see where these things trade off. But certainly, if we knew what algorithm would be run on a machine, in 2 years, what's a really good algorithm to run that would help everyone designing everything? Personally, I think we're not going to figure out the algorithms before we have the machines, and so it is a little bit of a chicken and egg problem. But before I go deeper into optical interconnects, I just want to give a sense of what we don't know. And so I'll look at Rydberg arrays. So Rydberg arrays, what you usually think of is a bunch of atoms in a lattice, and they interact through a Rydberg interaction, which is essentially we excite the atoms to a Rydberg state, and they interact through the Rydberg blockade. The blockade has a certain radius, and in principle that allows for long-range interactions. So if you think of qubits on a grid, you might think we're in a problem because the qubits that are far away from each other are not going to be able to interact. But with Rydbergs, presumably we can do these long-range interactions. And so the question is, how big of an array do you want to make? And people believe that they can get arrays of about 10,000 qubits, so 100 by 100. Hasn't been done yet, but this is widely held belief. But is that useful? And so in order to get a 100 by 100 array, you kind of want really long range interactions. And we studied the sort of advantage of having these long range interactions. The problem is, as you're going to a higher Rydberg level, you become more sensitive to electromagnetic fields. And you can never control your stray electromagnetic fields perfectly, and so you're always going to have some kind of noise there, and you're going to be more sensitive as you increase the radius. And what we showed is that if you only consider that type of noise, let's say everything else is perfect, then going to a larger radius is not worthwhile. So what you're seeing here is the fidelity of an interaction as we go. So we're interacting between qubit at site 0, 0 and qubits at other sites. We're looking at how the fidelity of the interaction drops as we're going further. And the reason this is always the same is that the algorithm can kind of make a choice. Do we use a long range interaction, or do we use swaps? Do we move the information around, do the interaction and move it back? And each time we move something, it costs us 3 C0. So if we want to do a C0 between two things that are far apart, we have one option, do the longer range interaction. And the other option is do a bunch of other C0s in order to get the information flowing from one side to the other. And we see that the algorithm, regardless of what's the maximum allowed radius, it always chooses to do these swaps because that's just a better choice. And then we added some noise. We said, what happens if there's other sources of noise? And you can see that in that case, slightly longer range interactions do make sense, but it does stop at fairly low interaction radii. So it's very unclear if going to higher Rydberg states in order to create long range interaction in these grids is going to be useful. And that means our 100 by 100 grids where getting interactions from one side to the next so difficult, do they make sense, or do we want to focus on a smaller grid that's maybe 10 by 10? So again, open question. No one can give a good answer to this.
I have another question in the chat related to these noise levels. Maybe this was already answered, but this is from a PhD student of ours, Chris Long, who says, I would expect the noise levels to tend to a steady state as the processor is increased in size due to the locality of the physics producing the noise. Where does this intuition break down?
Yeah, so it's true that the noise does is more localized, but that's only under the assumption that we have very short range interactions. And so in Rydbergs, for example, that is somewhat true because we can turn the interactions off when we want them to. But more generally, we have unwanted longer range interactions, and it's true as the processor grows, the qubit in location 0, 0 might not have a huge influence on a qubit 9, 9, but now you have a connectivity problem, right? So you've traded off noise by creating a connectivity problem. And in a sense, this is where you want to go to optical interconnects as opposed to other interconnects. Because optical interconnects allow you not only to connect computers without having them interact in an unwanted way, but also they allow you to use optical switching to maintain a fairly high connectivity map. Now, that being said, people have thought about doing things with low connectivity maps, with surface codes and things like that, but that creates big problems. So we kind of know that surface codes, for example, they don't scale very well. They require insane overheads with a number of qubits. And we can get around that by having long range interactions. And so, the rest of what I'm going to talk about is about modular quantum computing with optical interconnects. And maybe I'll get to the point which this should be like the biggest takeaway. If you've never thought about optical interconnects, then this is the slide you want to remember. And so now we want to use photons to exchange quantum information. And the problem is, there's two big problems. The first one is that it's really, really hard to get information from a qubit, from a physical qubit that's not a photon, into a photon, because photons don't interact very well with anything. And so, getting that information across is hard. The other problem is that quantum information is very fragile because we have a no cloning theorem. So we can't amplify things. We can't transmit the information, and if it fails to reach the other side, we kind of try again. That just doesn't work. And so we need a workaround. We need a way to do this without taking a huge risk and without requiring interactions that are hard to generate. And the way to do that is by heralding entanglement. So we basically get the interconnect not to move the information from one side to the next, but rather it creates entanglement between two cores. And now we're going to use things like teleportation to transmit the information from one side to the other. And so, if there is one, huge takeaway message from this talk is that optical quantum interconnects herald quantum entanglement between cores. They don't move information around. And so now we have another problem of how do we use that entanglement to move information. But now we're very different from a classical problem of networks. How does it work? Very, very generally, we emit a photon from each one of the qubits in two different QPUs, and we get these photons to interfere at a beam splitter and do a Bell measurement. And this has been demonstrated in ions, and it's been demonstrated in a couple of other systems. But let's say the one that's most promising for an actual quantum computer is ions. Extremely slow. I'll do this slide quickly and go to the slightly more technical slide. So this is an experiment that was done in Oxford a few years ago. This is the state of the art at the moment. So what you do is you emit a photon in two different modes. For simplicity, let's call them H and V. It's not actually H and V, but so horizontal and vertical polarization. And then you take these photons that are entangled with the atom. So you either go to decay to one channel and emit one photon, or even decay to another channel and emit a different photon. So you're entangled now because this happens, different probabilities. You can see that the probabilities here are not 50-50, but that's fixed when you enter the fiber. And then you do this Hungo-Mandel type experiment with this Bell state analyzer. And what you're looking for is two clicks. So you want two of these detectors to click. And what's great is, let's say a photon is lost along the way, then only one detector clicks, and you just say, okay, I didn't succeed. Let's try again. And so you just repeat until success. So this is a highly probabilistic process. It happens with success of less than 1 in 1,000. But eventually you can get quite a lot of photons, rate of about 182 hertz in terms of number of photons or number of pairs are created. So 182 pairs per second on average, right? But again, highly non-deterministic. So sometimes you might wait a long time for a pair. Fidelity is, in this experiment, is 94%. And most of the loss in fidelity is actually things that happen to the atom as you're trying to do the measurement in order to recover in order to measure what entanglement was generated. So the actual optical part here is very high fidelity. There is another piece with this Bell state analyzer that's also very hard to align, and it creates another drop in fidelity. But in principle, you can get extremely high fidelities here. Let's say 99% is definitely achievable. And then in terms of rates, using a method like this, you might be able to go to about 2 kilohertz, but probably impossible to go faster than that unless you start doing things like multiplexing, things like that. Questions?
No questions so far. I think everything is either
Okay.
clear or people are still typing away.
Extremely confused. Okay.
Yeah.
Okay, but maybe the important piece here is this is very slow. Okay, so if we think of an ion trap, 2 qubit gates in an ion trap are about a 1/10 of a millisecond. They're about 100 microseconds. And we're talking about under a millisecond or more than a millisecond to create a pair, right? So in fact, 5 milliseconds in this case. It's very slow. It's about 2 orders of magnitude slower than a 2-qubit gate. And like I said, we can get it to about an order of magnitude slower than 2-qubit gate. But that's under the assumption that 2-qubit gates don't run faster. The other piece of information that you might want here is that T2 is about 1 second in these kinds of systems. Or let's say 1 second is kind of a realistic T2.
This fidelity, we've got a question here. This fidelity of 94% that you quote, is this the average fidelity or some best case?
That's a good question. I'm not 100% sure, but I think it's the average fidelity. Yeah.
Okay.
This is, we just do a lot of tomography and figure out what the state is. Yeah. So now the question is, when does this become useful? Because we have this very slow interconnect. It's not, 100% fidelity. Is it useful? Do you want to even use it to connect 2 quantum computers? So you now have these 2 quantum computers. They're not that great because everything we have is not that great. And you're adding another piece of equipment there that makes it, in a sense, even worse. Is that worthwhile? And the way to analyze this is to say, let's take an algorithm and try to solve it and assume that algorithm requires more qubits than what I have in one machine, and assume I have 2 machines. So now I can use these 2 machines separately to do some kind of trick in order to get the algorithm to work, and people work on these methods. Or I can use my not so great interconnect and try and make this work. And so the very first thing we did when we started Entangled Networks is we tried simulations to see if this works. And so we took a VQE algorithm. The reason we chose VQE is just that it's a fairly popular algorithm, and it's fairly easy to create something that's very specific to a dual core system. So now we have two different cores, and we're trying to solve a 12-qubit problem on 2 cores that are 6 qubits. And one way is sort of just, let's do it in the simplest way. We'll just run the variational algorithm on each core separately and get a result, and just connect these results in the best possible product state. And this is what we see in dark blue. Again, this is a VQE, so the idea is to try and get to the exact solution. What we're plotting is the distance from the exact solution. It turns out that we can get a certain result. Now, the next question is, what if between these variational runs we do an interconnect? And in principle, we could get so this is a very, very good ansatz, and so it would give a perfect result. We could get to the exact solution. But what we did here is we penalized each time that one of these gates is used. We just added decoherence on top of the result. So as you're waiting for the interconnect to work, you're decohering, and what you're seeing is we're not at the exact solution. We're getting a big penalty, but again, we're a huge improvement over these 2 cores working separately. And then we said, can we compile this in a better way, move things around a little bit so that we don't suffer as much from decoherence? And the answer is yes, we can do that and get improvement. And overall, it's a 10-fold improvement, so quite substantial. Taking this result, we kind of saw that the optimal number of interconnect uses was 3. As we go to more than 3 interconnect uses, the penalty is just too high, and so we're getting worse performance. And so we said, what can we do with just 3 interconnect uses? And so we took the entire range of transverse field Ising model and looked at what happens there. And so we can see the best product state versus the variational state that we get from one of these things, but only using the interconnect 3 times. And in order to get these on the same plot, we had to reduce the error on the product state by a factor of 10. So you can see that we're, in some cases, a couple of orders of magnitude better using the interconnect. So this is very promising. It means that we don't need to use the interconnect too many times in order to get an advantage. and it makes sense because each time we use the interconnect, we essentially double the Hilbert space because we're creating twice as many Schmidt terms between these two cores as we had before. And so this works very well, both in theory and in simulation. It's in practice, no one's ever done this.
Just a quick question. This penalty rate that you apply to the interconnects, how did you choose it? Is it something that you expect to be realistically what the penalty would be for a given optical connection?
Yeah, perfect. So yes, so this is the penalty here is that the rate is calculated to be 1,000 times T2. So I said, in this experiment, they went to 182 hertz. We can probably push this to about 1 kilohertz, and with 1 second T2, that ratio of 1,000 to 1 is something realistic. Yeah, so that's a good question. So this is what we expect to be able to achieve with the device that we're developing. Yeah.
And I have another question from the chat as well. Could you comment on the decoherence model of the VQE?
Yeah, great. So we just took a very, very simple just T2 decoherence rate. I'm not sure that answers the question, but is that okay?
We'll see if I get a follow-up message.
Okay. I think I'm a bit behind on time, right?
Okay. Well, it depends how long you have left.
Okay, so I'll skip one slide, but I'll just say very quickly we did another work. It's very similar using Trotter for time evolution. But I kind of want to go into the results we have using our software. So what you need in order to get everything to work, these multi-core machines to work, is software at every level, from the algorithms, which is what I showed before, down to the compiler and down to the real-time stuff, because things are not deterministic, and now you need to handle this new type of paradigm where things are not deterministic in your circuit. So I just want to show what we did with the compiler. So we have a compiler that compiles for a multi-core architecture. And what the compiler does is it reduces the number of times information flows from one core to the next. So what we feed in is the topology. So you're seeing here two 8-qubit devices that are connected with these two channels. These channels could be an optical interconnect. It could be some other channel. It doesn't really matter for the compiler. And what we're trying to do is reduce the number of times information flows from one side to the other. And this is what you're seeing here. In dark blue is just a baseline circuit, which doesn't respect any topology. In light blue is what Qiskit does and how it compiles. And in orange is what our compiler does. And you can see that there's huge reduction. And what Qiskit does is it tries to just minimize the number of gates. Right? So we're not aiming for the same function. And so clearly, it doesn't take a lot for us to do better, but we are doing very, very substantially better. And what's kind of nice is that once you realize that you have this kind of topology, just minimizing the number of times we pass information across really gives you an advantage across the board. Now, what's nice about having this tool is that now we can do assessment on performance. And this goes back to the question I had before, and also this is my last or penultimate slide. So I'm about to finish. And this is, what kind of interconnect do we need more generally, and how does it affect different algorithms? So what we're seeing here is something similar to the algorithmic qubits that IonQ use to benchmark devices. And we're saying, what would happen if we took two devices and connect them together? These devices are modeled according to what IonQ have for their devices on Azure. So we took those parameters to model noise and things like that. And we did a full-on simulation of two algorithms. One is a quantum Fourier transform, And the second one is quantum phase estimation. I think it's the opposite. So triangle is quantum Fourier transform, square is quantum phase estimation. And we're measuring this volumetric benchmark, which is called the algorithmic qubits. So 10 qubit devices, we get up to 14 algorithmic qubits with an interconnect that has 1 kilohertz and 0.97 fidelity. And we can compare that to a monolithic processor with the same device. So now this is an infinite number of qubits, but we're limited by noise, and we can get up to 16. So, we took two 10 qubit devices, we went up to 14, we got an extra 4 qubits. And we're not doing much worse than a monolithic device. So the interconnect is not a huge bottleneck. And then we tried other parameters. So I'm showing one example, which is improving fidelity. What would happen if we improve fidelity? And we see that we get a very modest advantage. And actually, the biggest insight from this work is that the gate overheads that we require, because we're doing things like teleportation, remote gates, as we're moving information across one device to the other, those are the biggest bottlenecks. So it becomes very, very expensive just in terms of number of gates. So if there's one thing we need to improve now, is not the interconnect, it's really the 2 qubit gates. And so, just to finish, I would say that the biggest takeaways, one, I think the big takeaway that you should have is that, optical interconnects are used to create entanglement between cores, not to transmit information. And then, if you have good logical solutions, if you have good software, you can really boost performance and kind of get today's state-of-the-art technology into a quantum machine to improve performance. But of course, the trick is getting 2 quantum computers to connect, and there aren't many quantum computers around. Yeah, thanks.
All right, great. Thank you very much. So we have a few more questions. I'm actually going to see if one of our students, Chris, will be promoted to a panelist, because I think these questions lend themselves well to a little conversation. But the first one is related to this decoherence model on VQE. So you mentioned that this was mostly T2 noise. So was the T2 noise added as a CPTP map after each gate, or was the noise incorporated into the gates themselves?
Yeah, so no, so it's added as a CPTP map after each one of these remote gates. Yeah.
All right. And then, Chris, do you want to ask your optimization question?
Yeah. So with the you took like this network with some topology and some connectivity. When you optimize this, is this just kind of assigning weights to each edge in the topology given by the number of operations that are across it, and then doing some max cut solution? Or is there something more complicated going on here?
It is very, what you're saying is very close to what we're doing. It's really getting this kind of mix cut. The trick, the part where it becomes tricky is if you just look at the circuit, then you're missing the time information on sort of, maybe you're getting like this great mix cut solution, which would reduce, the number of interconnects, but maybe you're moving information from one side to the next, and it's going to be used there, much later in the circuit, and it's much better for you to leave it where it was and pay the price later in the circuit. And so we kind of, the big innovation there is really understanding how to deal with the time, the thing that the circuit actually happens in time. And roughly the way we do it is we look at, we start with a global scheme where we do exactly the max cut, and then we start looking at windows and optimizing over those windows. Yeah.
Okay, that makes sense.
But essentially, it's a max cut problem, or it's a constrained min cut problem.
I think while we were
precisely,
I missed the answer to the question about how the noise model is working. I'm not sure if we got to that or not while we were reading.
Yeah, so the answer is the noise model we used for the VQE is just each time we have one of these gates that goes from one processor to the next, we just add a CPTP map
Okay.
on top of it. And it's done with Qiskit. It's fairly simple to do. But in this case, we use a more complicated noise model, which is applied after essentially each gate.
Okay, so in one you're applying it at the end of the circuit, and this one you're applying at the end of each gate.
So it's not at the end of the circuit; it's just at the end of each one of these remote gates. Each gate that goes from one process to the next.
Right.
Whereas here we're penalizing every gate according
okay.
to its own specific noise model.
Okay. Thank you.
I also have a question. Could I ask it now?
Yeah, sure. And we've got a few more questions from the chat, but go now. Yeah.
Yeah, I'm wondering. For example, you have two QPUs, but in your like map, you show the connection between the two QPUs by ZZ gate. For example, I want to do some operation, like not ZZ operation, do some other operations. For example, between some qubits in the QPU 1 and some qubits in the QPU 2. How you do that?
Yeah, so that's possible in this model that we have here. So in the previous VQE we did ZZ gates. Here we're doing either teleportation, you can just move the information from one to the next, or remote CX gates, so remote CNOTs.
Yeah.
We also have methods, but that's not implemented here, for doing more complex operations and multi-qubit gates, but that's far less developed. Yeah, you can use more intricate resource states and things that are much more complicated to do more complicated remote operations.
Yeah, for me, like you only connect, for example, the last qubits in like QPU 1 and the first qubits in QPU 2, right? And when you want to do, for example, I want to do like the second qubits in QPU 1 and the third qubits in like a QPU 2, I want to do the operation between these two qubits, then you need to swap it or like to change your to add more gates to accomplish it. That means your gates, like the number of the gates you would like to use will be like more compared to like if you have 40 just in one chip like a QPUs, right?
Yeah. So if you don't have all-to-all connectivity in one of these QPUs, then things become very, very complicated. We did do some work on that, but it becomes messy. It becomes a lot more messy. But the nice thing about ion traps is that they do have this all-to-all connectivity, and so the model works really nicely here. But yeah, it's a much messier model if you don't allow it.
Okay, thanks.
All right, thanks. Yeah, we have a few questions in the chat about the technology. I think I'm gonna ask them all at once, and you can answer them. So, how far is interconnect technology from superconducting platforms or optical platforms or other frameworks for quantum computing? And what do you think is the first platform that will enjoy this? And as a slight follow-up question, what would your interconnect technology, or would your interconnect technology be compatible with cluster state computing, like some of the things they're looking at PsiQuantum?
Yeah, so our technology is not compatible with fully optical quantum computers like PsiQuantum. The reason is that our entire thinking is based on qubits that are sitting there and they're waiting. But in terms of what's the first viable technology to have that, I'm fairly sure PsiQuantum already know how to connect processors. This was on their roadmap essentially from day one, and so they know how to do it. There is a huge problem there because photon loss, because qubits are not sitting there and waiting, photon loss is a bigger issue. In terms of physical other physical qubit implementations, ion traps are certainly by far the closest technology in terms of having a computer that runs on the one hand and being fairly, let's say, easy to interface with optics. So this experiment from Oxford that I showed, it was with ion traps. Superconducting is much harder because you need to convert from optical, from microwave to optical, if you want to do a proper optical interconnect, and that technology just doesn't exist. I mean, people are making progress, and it's insane physics, but it's hard.
Yeah, okay, and I have a little follow-up question regarding technology as well. So how would you envisage these interconnects being compatible with hybrid systems if you had one platform communicating with a different standard? Would this be possible? Or even just backwards compatibility, if you have an updated system that uses a slightly different frequency, that operates in a different regime, could you link it up to your network of interconnects, or would this linkage only be available for an equal technology?
Yeah, so that's a fantastic question. It is really hard. And the reason it's really hard is we need to convert frequencies. We need photons to be at the same frequency in order to do this. And we also need to match the modes. So if we're using sort of the standard methods for doing the Bell measurement, we need things to be in the same mode. And so, the shape of sort of the wave function is important. And so there are many challenges. Now with ions, even different generations of machines are fairly easy because, as long as you're using the same ion, photons are going to be the same. There's much less variation between machine and machine. Of course, if it's a different ion, then you have a problem. With other technologies, it does change quite a bit.
Mm-hmm. And so, given these challenges with updates, would you think that it's, even though it's challenging, it's worth looking into, or is the solution more just make sure that all your QPUs are the same? And
I think eventually, my personal belief is that in 20 years we'll have quantum computers that have different modalities.
Yeah.
Yeah.
All right. Well, I don't see any more questions in the chat, and this has been our hour exactly.
Yeah.
Very good timing. So yeah, thanks again for giving this talk. This was really great, and it's always nice to have these talks where we can interrupt throughout. I think it helps everyone really follow and understand everything as we go.
Yeah. Definitely nice on my end.
Yeah, it makes it more engaging, especially on Zoom when you can't even see your audience. So yeah, really huge thanks, and if ever you come by Cambridge in the UK, definitely do email us, and we'll give you a lab tour and take you out for dinner.
Cool. Yeah, thanks. And I can be reached by email or Twitter or LinkedIn or whatever. So if anyone has questions, I'm very easy to find.
Okay, great. Well, thank you very much. And for everyone in the audience, we'll see you next week.